Greetings, my name is Mark Smith. Fault seal and permeability prediction in the subsurface is a major problem for industry, where up to 70% of reasons for well failures have been attributed to fault seal and seal issues. In this paper, we'll describe our approach to this issue and show how our models calibrate with complex faulted fields. This forms the basis for forward modelling. In the subsurface, fault can leak via porous and permeable host and fault rocks, or via fracturing in the host, damage zones and fault cores. A single fracture can leak a field over a few thousand years. In addition, there is an enormous amount of variability that can occur along short distances on faults. This is displayed here in the De Rossa example from Miri in Borneo. So with drilling, it is very unlikely that critical leak points would be sampled to provide quantitative data across a whole fat trap seal surface. As such, fault seal and permeability analysis is a low knowledge area. To fully risk fault sealing, an assessment of all possible mechanisms of seal failure should be undertaken, and this is the philosophy that we are pursuing here. It is very important that any fault seal and permeability models developed are well aligned with fault development models. What we do is quantitatively differentiate between successful and failed seals in juxtaposition, in fault damage zones, in fault rock, and with the consideration of through-going slip surfaces. The components of the method are firstly an empirical lithologic data set. We can demonstrate that effective inter-seal lithologic composition ranges differ between upthrown and downthrown faulted rocks, for example. The second component is the seal quality algorithm, the seal index, and this is used to identify brittle, potentially leaking and plastic seals. And thirdly, we have a permeability and threshold model for each host and fault rock component, and this provides the limits on the hydrocarbon column heights. All these components are integrated into a 3D model where a range of possible fault sealing leaking mechanisms are tested in calibration to faulted fields. Importantly, we initially make no assumption as to what the sealing mechanism is. And the results of the calibration exercises and the uncertainty and the variance that we see in the models is then the basis for any forward modelling. Here I've jumped ahead to show you where we're going. This is a calibration study on a fault block in the Flounder field. In subsequent slides I'll explain how we get to this point. What we're seeing on the left is the faulted anticline map, and fault block 6, that's the one that this model is about. On the far right we have a petrophysical log showing an interbedded sequence of sands, coals, silts and claystones, and with variable reservoir fill with oil, water and gas sands. In the centre we have a modified Allen diagram. There are coloured polygon outlines that outline the existing hydrocarbon columns. You can see them in the various colours, and in light green we have model columns, and in dark green downthrown model columns. The panel to the right of the Allen diagram shows the cross-section through the central part of the fault blocks, showing model hydrocarbons in green, good seals in the brown colour, poor quality seals in the grey and reservoirs in the yellow. The black sigmoids on either side show the dip spill levels on either side of the fault, and with all this data we're effectively setting up a 3D model. The results here is they were explaining all the hydrocarbon and water bearing sands. We have a pretty good match of predicted versus actual column heights. The model fault throws match very closely also with the seismic fault throws. Empirical data has proven to be a very powerful tool in differentiating working and failed seals. Here we're looking at cross plots of footwall and hanging wall seal tolerance levels for two lithotypes. You can see in the center panel the hanging wall seals are very sensitive to the proportion of the lith1 fraction. In contrast, the footwall seals have a much higher tolerance level. The seal quality index that we use is a composite measure derived from petrophysical algorithms and the empirical lithologic data. It is in effect a modified V clay which discriminates plastic from more brittle seals. The plot in the centre of the diagram shows the sort of issues that have to be addressed in showing the range in clay type responses with burial. You can see the illitization process there, which fairly dramatically changes V clay, and then I've put a kaolinite example at the bottom there to show the range there as well. The plots on the right show the logs used to derive the seal index. On the far right we have a seal index, and we represent that as a histogram for each seal interval. Looking specifically at the 3070 and 3080 sample points, you can see that the V clay for both of these is very similar. What's different is that the 3070 has a much higher neutron than 3080, and it also has a lower density than the 3080. This translates into a higher seal index with a much higher potential for that zone to be more plastic. This shows a calibration exercise in a West Tuna well with a gas column in red and an oil column in green. The gamma ray is reasonably high through all of the seals, but the seal index profile, as you can see, is quite variable. Model A, it tests pure juxtaposition, and where there is juxtaposition of shales on either side of the fault, the model generates in light green a hydrocarbon column. And what you can see in case A is that there is not a very good match to the actual hydrocarbon distribution. In model B, we adjust the parameters, so not all of the seals are working, and they're highlighted in the grey. And what you see here is juxtaposition working, explaining the upper gas sand, and there's a intra-column pore seal there with very little pressure differential across that, and lower you have the oil column working, and there's no other hydrocarbon columns generated. So this is a pretty good match, but the column heights don't match so well. In model C, we have differentiated juxtaposition plus a little bit of smear highlighted in the red circles. So why is this happening? When you look at the seal intervals and then plot it out against Young's and Poisson's ratio, you can see that the higher seal index seals are more plastic, and the low ones stiffer and brittle and more prone to fracturing. So differentiating brittleness is key to achieving good calibration. And what we do in the exercises is to adjust. You can adjust fault throw, you can adjust cutoff parameters, etc., in order to find the best fit in this setting. It's significant perhaps here that the maximum stress in this setting is near horizontal. In other settings, different parameters and different cutoff values might apply. What you have seen here is a simple fault throw sensitivity model on that West Tuna well. And what you can see is the uniqueness of the best fit fault throw solution, which matches up pretty closely with data from seismic mapping. We also test SGR. SGR assumes that gouges are always present as a continuous unit on a fault plane, and that the gouge properties are the main control on hydrocarbon column height. To physically comply with the SGR formula, summing slipped interval clay at points on a fault plane, the gouge generated must stay at that location, accumulating and homogenising slipped intervals material as the throw increases. Field data shows this just doesn't happen. Frictional forces that generated the gouge always cause fault rocks to move in the direction of throw, so any gouge is in the wrong spot. The SGR method ignores other fault processes that play a role in fault seal, e.g. fractured fault core or damaged zones or host rocks. This movie tests an FSGR model, frictional shale gouge ratio, where once the gouge is generated in the fault core, it continues to move down the fault in the direction of throw due to ongoing fault friction. You can see here that the match isn't very good, and on that basis this model fails. In the bottom right you can see the difference between the FSGR and the SGR plot, where any gouge generated is moved down the fault at roughly half the throw for any point. In faulted structures where the seals are relatively thin, it's important to consider the lateral continuity of the individual seals. To do this, we look at existing fields in the similar facies, and we look from multiple wells in that field at the lateral continuity of individual seals and how they vary in thickness and quality over the field area. This data establishes a range of lateral extent or Dmax values that are put into the model, and in the bottom right you can see marked is how we manage that by putting a break in the individual seals. And what you see there is where the seals are thinner, there are a lot more breaks, and that is consistent with that facies. Our permeability modelling is a combination of the models of Sperovic and Revel and Cathlays. The Sperovic model was the first to quantify the shift in V-clay versus permeability relationship with depth for host and fault rocks. Importantly, this was only for data for V-clay up to 40%. The model also does not take into account fault rock grain size and sorting. The Revel and Cathlays demonstrated that in sands, your permeability reduces up to around V-clay 0.4, at which point the permeability increases. The permeability trends in the low V-clay zone of Revel and Cathlays are dependent on grain size and sorting, as you can see in the diagram on the right. The bottom right diagram shows where we've combined both with a backdrop of the Revel and Cathlays data. Here we have set our model at the midpoint of a depth range of a well that has shear zones. Overlain on the model is NMR data, and what you can see are discrete clusterings of data, particularly over V-clay 0.4. You can see highlighted in the purple discrete populations of data clustering around the fault rock curve, and similarly for the host rock curve there's a separate gradient showing a slight increase in permeability to higher V-clay. This data in subsequent slides is plotted onto the well profile in depth, where you can identify the different shear zones in the well. This well is located on the flank of a salt structure with beds dipping at about 30 degrees. There are 3 separate oil columns, B1, B2 and C, separated by shales. The boundary, the top seal for column C fits with a shear zone. It's a very thin unit, and within the thicker shale below there are shear zones identified in that as well. This is another example, this time in a fairly sandy sequence. You can see on the Perm v clay plot a number of points there down in the fault rock area. There is a fault identified also on the dip meter data that coincides with this data point, so there's good calibration there. And there's also a shear zone with fractures identified on the dip meter log. There's higher perm in the vicinity of those fracture zones, so perhaps we're defining the extent of a damage zone in this case. This is a case where argillaceous silt to very fine sand sequence, when faulted, traps a 120 metre light oil column at fault A. Looking at the plots on the top right, you have V-clay perm, and you can see the points associated with the fault model. And in the well, you can see over a 60 metre interval a number of deformation bands and slip zones. The column heights here in the model all show column heights up to about 200 metres. So this model explains quite readily the occurrence of hydrocarbons in this area. The V-clay permeability model that we use is linked to depth, and here we can see the models showing the trends for fault rock and host rock as previously described. And what we're showing on the left is a silty claystone interval with high V clay, and you can see a mismatch of that to the host rock trend. Now to the right, if we adjust the depth of the model, we get a very good fit. And what is implied here is that what we're seeing is evidence that that sequence had been buried significantly deeper, and in this case about 300 meters deeper, and has subsequently been uplifted. And when we do that, we get a very good match with the data with the host rock trend. On the right side there is a similar story. This one's in the Gippsland Basin, and this shows the match where we have a good match to the gradient of the high V clay units with the host rock model, and this requires an uplift of about 800 meters. So what we're seeing is a tool here that can help us identify areas of uplift, and that has fairly big implications on establishing porosity, permeability trends on a consistent basis across a field where you would often not know which well had been uplifted or not. To estimate column heights, we use a threshold pressure V-clay relationship that's linked to our permeability V-clay functions. Here we're showing threshold pressure for V-clay from Gippsland Basin Lakes Entrance Formation wells. And what's interesting is that there is an inflection point at about 0.75. Our view here is that in the range 0.4 to 0.75, during compaction, what occurs is a pincer movement between the compacting sand grains, compressing the clays and reducing permeability and increasing threshold pressures. Once beyond 0.75, there's less sand involved and the threshold pressures drop away. This slide shows how we build a 3D model. We integrate all of the seal distribution, smear extent, etc. and permeability for either side of the fault. In this case, we're looking at manta again, which is a down-thrown fault trap. And on the right, you can see in the polygons the distribution of the different hydrocarbon columns. The top row is the host rocks. So you're seeing the permeability distribution here for the upthrown and the downthrown side. The second row is the fault rock. So this shows the permeability that results from the smear extension of the better quality seals, and also the permeability of the fault rock in reservoir and the seals. So there's a lot more blue there, where blue is the lower perm units. On the right you have the downthrown section. In the bottom right we combine all of the data, and here you can see in the fault plane the fault rock permeability distribution, and you can identify in a few of those cases where the leak points they coincide quite well with the high perm or yellow windows. The bottom left is the juxtaposition diagram, which identifies where the fracture zones are. These are those grey hatchet zones. So all of this data has got to be put together to build a 3D model, and this is done in XYZ grid and can be plugged into a simulation model. The key conclusion here is that it's not one single factor that is controlling the sealing and leaking. It's a multiple set of factors, and all this work needs to be done before we can firstly explain the hydrocarbon distribution, and then go forward from there to look at flow models in this setting. This is a zoom in on the manta field, columns 6 and 7. At A there is a water sand, and looking across to the Allen diagram and the cross section, you can see that it's juxtaposed across the fault is a poor quality seal marked by F. At the top of column 6 there is a good top seal, and below column 6 there's a good base seal. The top of column 7, good top seal, and within column 7 there's a number of poor quality seals marked by F, and these don't generate pressure differentials through the hydrocarbon column. And below that there's an oil leg. So overall there's a very good match of model when you look at this in detail. What we're looking at here are two pore fit models for manta. The first is seal differentiation but with no smear, and what we end up with here is a pore fit of predicted versus actual, where the model columns are significantly less than the actual columns observed in the well. On the right we have the FSGR model, and the result here is that model overestimates the hydrocarbon column heights compared with actual. So these models are rejected on that basis. This is an exploration study. We have a prospect called Echidna located on the flank of a salt wall. At location B there's a collapse zone. The cross section is shown C to A, and that's shown in the Allen diagram, and we're modelling that with the Emu well and another well about 6 k's to the north called Piracuca 661. This shows the outcome, where we're getting a very close match of predicted versus actual columns in the Paleocene and Maastrichtian sequence. In conclusion, we find that good calibrations can't be achieved unless we differentiate between good quality seals that smear and the stiffer contingent seals that fracture in host damage zones or fault cores. Implicit in the models is that when smear growth ends after a few metres of throw, good seals continue to seal across through-going slip surfaces as fault throw increases. This is consistent with fault development models. Host rock threshold pressure limits for the same V clay are less than those for fault rocks and constrained calibration models. In the permeability V clay space, modelling defines host and fault rocks in wells and can, with NMR data, independently locate in-bed shears, faults and possible damage zones. Field static calibration models define leakage over a geologic time frame, but importantly provide a base for short-term time frame dynamic modelling, where you have the distribution of the low and high perm rocks identified. The close alignment of this method with fault development models with the software that allows testing of many possible sealing and leakage models has shown consistently high levels of calibrations in wells around the world. The application of this method is likely to be beneficial for oil and gas, carbon capture and storage and groundwater studies. Thank you very much for listening. This slide summarises the results of a 10-well integrated calibration exercise on discoveries and dry wells in the Bonaparte Basin. The examples shown in the next two slides are for the Corallina oil discovery and to the north the Claudia well, which was a dry well. Here the Flamingo group provides a generally pretty good quality seal over hundreds of metres. There are zones near the base, relatively thin, that are poorer quality, and in the model on the right, the Allen diagram, where you have the darker brown, that's good seal on good seal, you can see that there is a leakage pathway to the left through the fault damage zone, providing a fracture pathway controlling the column height. The dashed line is the actual column height in the well. At Claudia, the seal section has degraded and there are larger sections where you have damage zone seals that are likely to fracture. You can see that expressed in the neutron and density logs in the panel on the left. On the right, and that's put in an Allen diagram, you can see that only a small model trap is generated right at the crest of the well, partially in a damage zone, thief zone. The well was drilled about 20 metres down dip from the crest, so that wouldn't be seen, but there are clear leakage pathways up through the sequence in that well, easily explaining that as the reason for well failure in this setting. Generally there's a degradation in seal quality as you go from wells in the south to those in the north, and this reflects general facies change moving to the north away from the continent. In summary, thank you very much for viewing and listening to this presentation. If you have any interest in our services or software, We would be delighted to hear from you. Please contact us if you have any questions, and we'll go from there. Thank you very much.